Hello! Today we're going to take a look at 2.2, angle properties of triangles. Now we are going to take a look at triangles and we're going to start by classifying them into two different ways. One of the ways that we could classify triangles is by their angles and the other way by their side lengths. So let's take a look at their angles first. So this first triangle is called an acute triangle, and that acute triangle looks something like this. It's when I have a triangle in which all three angles are less than 90 degrees. So like any triangle, all of their angles are still going to sum to 180, except now we make sure that every individual angle is less than 90. So this is an example of what one of those acute triangles could look like. The second type of triangle that we have here is an obtuse triangle. Now, a triangle that is an obtuse triangle will have exactly one angle that is obtuse, which is greater than 90 degrees. Now, it is impossible to have an obtuse triangle that has more than one obtuse angle for a variety of reasons. First of all, if we had two obtuse angles and tried to fit that in a triangle, I wouldn't be able to get my three sides to close. So if I start by drawing one obtuse angle and then I tried to draw a second one, I can't get those two sides to touch so I could close that triangle up. The other reason is if I have two obtuse angles in my triangle, I have two values greater than 90. Well, if I add two numbers greater than 90, I'm already over 180, and I haven't even made room for that third angle. So an obtuse triangle will just have exactly one obtuse angle. We all are very familiar with a right triangle. For the same reason as an obtuse triangle only has one obtuse angle, that still works with right triangles. It's not possible to have a triangle have more than one 90-degree angle. A, it wouldn't close, and B, it would add to over 180 if we threw in a third angle. Right, so here we are going to have one right angle and two acute angles in there to make up my right triangle. Now, something to note is we're drawing them in ways that we're used to, but they can be oriented in different ways and still tackle that same definition. So even if it's not in the position like this one is now, it could still be classified as right, obtuse, acute, etc. Now, oblique might be the one definition that we are not necessarily familiar with. We don't use it as frequently. But oblique simply means that it is not a right angle triangle. There is no 90-degree angle, no right angle inside my triangle. So that can be acute, that can be obtuse, that can be equilateral, it could be any other type except for a right triangle. So we've got many, many options here. So oblique simply means that it is a non-right triangle with no 90-degree angle. All right, so that was how we could classify triangles by their angle measures, but we could also classify triangles by their side lengths. So we have we have three different types of triangles that we can classify based on their side lengths. The first is equilateral. Now, we might be familiar with the word lateral if we're talking about anything like exercise-wise or physical activity-wise, or just like shapes, I guess. Lateral itself refers to sides. If I'm doing a lateral movement, I'm doing a sideways movement. If I'm talking about lateral area of my cone, I'm talking about the sides of my cone. So when I'm talking about an equilateral triangle, equilateral generally means equal sides. So a triangle with three equal sides. Now, as I'm drawing this here, a couple things to note. We talked about how at the beginning of the unit in our review section, we said that angles will always be opposite their correspondingly sized side length. So a large side length will be opposite a large angle, and a small side length will be opposite a small angle. So an equilateral triangle has equal sides, which means they're going to all be opposite equal angles. So all three of these angles are going to be equal in size. Sometimes people refer to equilateral triangles as equiangular triangles for the same reason, right? If I have equal sides, I must have equal angles. Now, we can actually figure out what the measure of those angles are because we know all angles in a triangle add to 180. 180 split three ways is 60 degrees a piece. So all three angles in an equilateral triangle will be 60 degrees. The next triangle type that I could identify by its side lengths is an isosceles triangle. Now, an isosceles triangle here has only two of those three sides equal. So let's say it's these two here. The third one is unique. You might be noticing I'm drawing these tick marks on them. So an equal amount of tick marks imply that the side lengths are equal, kind of like parallel lines, right? If we had that parallel line symbol, the same amount of extra arrowheads on my line implied it was parallel to another line that had the equal amount of extra arrowheads. So here I'm drawing one tick on both of those equal sides and two ticks on that one that's different. Now, just as before, we were saying that equal size side lengths will be opposite equal sized angles. So these two angles here opposite my two equal sides will be equal to each other. Okay? And this third angle that's opposite some unique side will be unique to the other two angles. That's something that I believe a lot of people forget about isosceles triangles is they do remember that they have two equal sides, but they forget they have two equal angles. So don't forget, remember it. All right, last but not least, we have a scalene triangle. A scalene triangle is one that has no equal sides. So in conclusion there, I guess if we have no equal sides, they're going to be opposite no equal angles. So if we're taking a look at what we drew above, this guy's scalene, three different angles, which imply I have three different side lengths. This guy's scalene too, right? So we're taking a look at those and we can draw something here that matches that description. Oops, there we go. Oh no. All right. So hopefully this makes sense that this guy here is scalene. We have three different sides, and I could indicate that with my differing tick marks. But also all three of these angles are going to be unique because they are opposite three unique side lengths. All right. After we've classified our triangles, we can move on to some properties of triangles. One of those first properties is something called non-adjacent interior angles. So, non-adjacent interior angles are the two interior angles of a triangle that do not share the same vertex as the exterior angle. So the interior angles of a triangle that do not share the same vertex as the exterior angle. All right, if you need some time, feel free to pause the video to get that down. But let's take a look at a picture. Now, what I'm going to do is I'm going to draw some things, I'm going to erase some things. So feel free to kind of just watch, but not copy down. So here, as we know from before, angle D, this one right here, is an exterior angle of a polygon, and in this case, the polygon is a triangle. Remember that an exterior angle is found by extending one side length of a triangle and finding that other side that's nearest to it. And that angle created on the outside of that triangle is considered exterior. The one inside is called interior. And exterior and interior angles side by side are supplementary. Now, if we're talking about D as our exterior angle in this case, and we want to find the non-adjacent interior angles, remember that non-adjacent means not next to. So angle A, B, and C are all interior, but C is next to angle D. It is adjacent to angle D. So when we're talking about non-adjacent interior angles, in this particular diagram, we are talking about angles A and B being non-adjacent interior angles to angle D. All right. Our goal is we are going to perform a proof. The proof is going to show that the exterior angle of a triangle, so in this case, angle D, is equal to the sum of the two non-adjacent angles of a triangle. So what it's trying to show, or trying to get us to prove, is that those non-adjacent interior angles will add up to equal my exterior angle. All right, for any proof that we do, we need a let statement. And that's what we're going to start off with. Our let statement actually already comes with a diagram. Our diagram is already drawn for us. Life is pretty good. So we are going to simply say, let the diagram represent a triangle and one exterior angle. Where angle D is the exterior angle. And angle A and B, angle B, are the non-adjacent interior angles. So really my let statement is just kind of representing and drawing or explaining that diagram there, right? I'm trying to prove something about exterior angles and two non-adjacent interior angles. So I want to make sure that my diagram and my let statement reflects that. Now, this proof is going to be a little bit different than ones that we've seen before. So if you don't totally understand why we're doing what we're doing at first, that is going to be okay. It's hopefully going to become evident. But we are going to follow the same general steps. So our steps are, after my let statement, I'm going to indicate my goal. Now, my goal, based on what the question has asked me to try and show, is to show that my exterior angle, in this case, angle D, is equal to the sum of my two non-adjacent interior angles. So I have the sum adding together of angle A plus B. All right. Now, we are going to use angle properties that we are aware of, and we are going to somehow use the transitive property. Now, there's not a lot of angle properties here that we can use. The only angle properties that I could maybe think of, and hopefully that maybe you can think of as well, in this particular case, is, well, I've got this supplementary set of angles going on, and that's something that maybe I can find useful. And I have angles in a triangle, and I know that all three angles in a triangle have to add to 180. Hold on. In supplementary angles, those add to 180. And in a triangle, all three angles also add to 180. So it might be useful to use those two properties because they're going to have similar outcomes there. if I can show somehow that angle D is equal to something, and the sum of angle A and B are equal to that same something, then I can use the transitive property to show that angle D is equal to that sum. So, that is going to be our game plan. I'm going to start with the fact that these two are supplementary. So I'm going to say, well, angle D is equal, angle D plus angle C is equal to 180 degrees. I know that to be true because they are supplementary angles. Now, something that I'll notice in my goal statement is that in my goal statement, I had angle D alone on one side of the equal sign. So what I'm going to do is I'm going to do some basic algebra here and try and rearrange the statement that I just wrote down to get angle D alone. So I need to get rid of this guy here. I do that by subtracting angle C from both sides. And I just simply rearrange that to get angle D is equal to 180 minus angle C. Again, reminder, we chose to do that because in my goal statement, angle D was alone. So it would be worthwhile to have some statement where angle D was also alone. So we'll describe what I'm doing here. I just rearranged to isolate angle D. All right, the next thing we're going to do is look at that next angle property that we're aware of, and that's that all three angles in a triangle add to 180. So I'm going to write that down. Angle A plus angle B plus angle C is equal to 180 degrees. And I'm going to justify that and say that angles in a triangle, a nice triangle, there we go, triangle add to 180 degrees. That's a fact that we know. And just like before, we did some rearranging so that our equation matched what we had in our goal statement. Now, our goal statement had angle A plus angle B alone on one side of the equal sign. So I'm going to move everything else to the opposite side. So that means subtracting angle C from both sides and ending up with angle A plus angle B is equal to 180 degrees minus angle C. So in this case, I rearranged. I didn't do anything crazy, but I rearranged to isolate for angle A plus angle B. Now, why did I do that? I did that because I want to see if angle D and angle A plus B happen to equal the same thing. Because if they do, then I could use that transitive property. So let's check it out. Angle D is equal to 180 minus angle C. And angle A plus B is also equal to 180 minus angle C. How exciting! That means, because if I have two things, angle D and angle A plus B, that equal to the same third thing, by the transitive property, angle D must equal angle A plus B. So I'm going to write that down. By the transitive property, angle D must equal angle A plus angle B. Super stoked. Now we need our aha statement. Now we can get that from our original question. It said, prove that the exterior angle of a triangle is equal to the sum of the two non-adjacent angles of a triangle. So I'm essentially going to say that same thing. And I'm going to say, therefore, the exterior angle is equal to the sum of the non-adjacent interior angles of a triangle. Which is super sweet. We can use those skills to add into what we know about our other angle properties and help solve for some unknowns there. So that's super duper exciting. All right. We are going to do a couple of other proofs because we really want to make sure that we know how to do some stuff. And we're going to take a look at this first example. So example 1, it says, use your knowledge of parallel lines to prove deductively that the angle sum of a triangle is 180 degrees. So just to kind of reword what the question's asking us, it's saying, use what I know about parallel lines to prove that all three angles in a triangle add to 180. Now, I thought I knew that, but I need to prove it somehow. Now, if I'm looking at this diagram here, I don't have parallel lines. So that could be a little bit of a concern, because how am I going to use my knowledge of those parallel lines? What I'm going to do is I'm going to make some parallel lines. I'm going to choose one side of a triangle, any side, and I'm just going to extend that side length there. And I'm going to draw a parallel line meeting at the vertex of the other part of that triangle there. Because if I did it anywhere else, I'm not involving angle A in any of my calculations, and I want to know that A, B, and C all add up to 180. So I want to make sure my parallel line, come on. There we go. My parallel line is including angle A, B, and C somewhere along or meeting those parallel lines. Okay. So here are my two lines. I'm going to label them. Here's line 1. Here's line 2. I'll even throw some parallel line symbols on there so that I could help remember. Those other two sides of the triangle end up being transversals. So I'm also going to extend those lines. It might help me, it might not. But either way, that way I have more angles to kind of make mention of. So here is the diagram that I'm going to be working with. Again, I'm just using my triangle already presented to me, but then somehow incorporating those three angles A, B, and C to meet up with my parallel lines. All right, we need to have a let statement. So my let statement is going to be something along the lines of let L1 and L2 be two parallel lines, and T1 and T2 be transversals that form triangle ABC. All right, let's write that down. Let L1 and L2 be two parallel lines, and T1 and T2 be transversals that together form triangle A, B, C. All right, now our goal is to show that all three angles in this triangle add to 180. So our goal is, there we go, to show angle A plus angle B plus angle C equal to 180 degrees. Now, I don't know about you, but when I'm thinking about angles adding to 180 degrees, other than all of the angles in a triangle adding together to give me 180, the other thing that I see or think of is supplementary angles. So if I could somehow show that A, B, and C are supplementary, that would be one way to show that, hey, those angles must add to 180, so my triangle angles must add to 180 degrees. Now I'm going to look for somewhere on my diagram that's somehow going to have three angles side by side, and hopefully I can show that those three angles are A, B, and C, which can then help me prove that my three angles add to 180 degrees. Now, I wouldn't look over here or over here, because in both of those situations, I only have at most two angles that will be supplementary together. What I'm really looking at is this area over here. A good option is that these three angles, this guy A and this guy, would be adding to 180. I can in theory also choose these three angles. They make a straight line. Those work. These three work as well. I could choose kind of any one of these lines and the three angles that make it up. One that would be beneficial with me is to make sure I'm including A there, because then I have less work to do. I don't have to show you if I choose these three that one of them equals A, because if I choose something that already involves A, I've got less work to do. So that's going to be my strategy. My strategy is going to show that I have three angles that are supplementary that will add to 180, and those three angles will be angle A, angle B, and angle C. So let me choose, for the sake of, some consistency here, the three angles that I have highlighted. And I can't start labeling them A, B, and C because I don't know what they are. So I'm going to just put some labels here as placeholders. I know what A is. A is already A. It came pre-labeled. I'm pretty happy with that discovery. Oh, it kind of looks like a smiley face. Nice. But I want to figure out what angle 1 is. Hopefully it's equal to B or C. And what angle 2 is. And if I could say that all three of those add to 180, I am set. And wouldn't you know, when I take a look at what I know about in my angle properties of parallel lines, angle 1 and angle B happen to be equal to each other. Why? Because those two angles are alternate interior angles of parallel lines. Alternate interior angles of parallel lines. Super stoked, super exciting. Now let's take a look at angle 2. Angle 2 and angle C are also alternate interior angles of parallel lines, which means they must also be equal to each other. That's super duper exciting. And just as I intended to at the beginning, I notice in my diagram that angle 1 plus, let's do that alphabetically. Let's do angle A plus angle 1 plus angle B all add to 180 because they're supplementary. Again, super exciting stuff. Now, this is all I need. I know that if, that's not a highlighter. I know that if angle B is equal to angle 1, I can just replace, hold on. I've made a boo-boo. Do you see my boo-boo? I meant to have this as angle 2. Let's fix it. All right, before I go into a deep dive of my description. My apologies. So angle A, angle 1, angle 2, all add up to 180. Now we're on the right track. Okay, now I could be excited. If angle 1 and angle B are equal to each other, I can just simply, with the transitive property, replace angle 1 with angle B. And If angle 2 is the same thing as angle C, I can just simply replace angle 2 with angle C in this equation with the transitive property. So, let's not talk about it anymore. Let's go ahead and do it. By the transitive property. Angle A plus, replace 1 with B. Angle B plus, replace 2 with C. Angle C are equal to 180. All right, we need our therefore statement. We wanted to prove that the angle sum of a triangle is 180. So let's say it. Therefore, the angle sum of a triangle is 180 degrees. Woo, exciting. All right, we have one more proof, and then we are going to get going with some different find your own angle measure questions. So let's do one more proof for good measure, and then be on our merry way. Okay, so this time we want to prove that prove that AB, that line segment, is parallel to CD. Which means we cannot make any assumptions that their corresponding angles, their alternate interior angles, or their alternate exterior angles are equal, because we don't know if the lines are parallel to each other yet. But if we can show somehow that the corresponding angles happen to be equal, or the alternate interior angles happen to be equal, or the alternate exterior angles happen to be equal, then we can definitely go ahead and say that they're parallel. So let's take a look at our diagram. Now, our diagram's already provided to us with all the information it needs. There's nothing that we have to kind of discuss or describe. It was a question given to us. So for our let statements, it's pretty straightforward. We're just going to say, let the diagram below represent our situation. Let the diagram below represent the situation. All right, let's try and find a game plan. Now, in question, this line we are hoping to show is parallel to this line. And to show it's parallel, like we said before, we can show that corresponding angles are equal. So I'm going to look for any corresponding angles within my diagram. These two are corresponding. Something that I could kind of go for, I guess. It's a strategy I could use, but I don't have any of those angles there, so I'm not super stoked about that strategy. These two are corresponding. Now that I don't mind too much, because I already have one of those those two angles. If I'm taking a look at those, right now, the green X's, those two angles there, seem like my best scenario, but the pink would work just equally as fine. I don't have any alternate interior angles that are already in my diagram, and I don't have any alternate exterior angles that are already in my diagram. So it's not that I can't use that strategy, it just doesn't quite seem worth it. Okay? So I'm going to go ahead and do my proof trying to show that these two angles, the 65 and this angle here, are going to be equal to each other. Now, I should name that angle just so that I have some context. I'm going to use X. Right? So when I'm trying to write my goal statement, I'm going to say goal, show that corresponding angles 65 degrees and X are equal. That's going to be the dream, the aspiration, what I look forward to. All right, now I have to figure out how to do that. Now, if again, I'm going to zoom in on that diagram and say, okay, I can't figure out x, and I can't just say it's 65 because I don't know those lines are parallel yet. So I'm going to somehow have to find out how to figure out the value of that particular angle. Now, something that I notice are my triangles that are also in this diagram, because this whole topic's about triangles. So if I have this triangle here, if I knew this angle, let's call it y, then I can say, well, if I know what y is, then I could say all three angles in that pink triangle I've drawn will add to 180, and then I could solve for x. Luckily, I could solve for y really easily because it's supplementary to that 105-degree angle. So I'm going to say that angle y is equal to 180 minus 105, which is 75 degrees, because it is supplementary to 105. That puts me in a really good space because now that I know that this is 75 degrees, this one's really easy to find. I know that all three angles must add to 180. So 180 minus 40 minus 75, that actually gives me 65 degrees. So that's 65 degrees because angles in a triangle add to 180 degrees. Now this is super exciting because I did not use the fact that those lines were parallel to prove that they were parallel. Because if I did, that would be circular reasoning. And I can't do circular reasoning, that's an error in proof. So I'm super stoked because I used all of the other skills that I have. Now, I need some sort of therefore statement. I'm not using the transitive property here because I actually know the values of all of these angles. It's a more specific example. But I'm going to still need that aha statement. So, my aha statement is going to be something along the lines of, hey, since 65 degrees is corresponding to angle x, and angle x is equal to 65 degrees, then the lines AB and CD must be parallel. Super stoked, super exciting. All right, if you need a moment to write that down, to copy things down, to gather yourself, feel free to pause the video, but we are going to move on. We've got 3 last examples, and we have finished all of our proofs. We deserve a little bit of a break, and this is the break that we need. So, example 3, determine the measures of the interior angles of CDE, the triangle. So I want to know these 3 angle measures. Now, what I'm going to take a look at is actually not naming them D, E, and C. Let's just practice naming them with the 3-letter technique. So if I'm going to take a look at, I'm going to look at this one first. I like it a lot because I can automatically see what I've got going on here. I'm going to name it angle CDE. And I could see that that's going to be 80 degrees. And hopefully you see that too. Why? Well, it's supplementary to my 100 degrees. Now, if you have an idea of what to do next, please take it away. Do the rest of the examples. Check if you're right. That's all good to go. But if you're stuck or you want me to walk you through, feel free to join for the ride. The next angle I'm going to look at is this one here, angle DEC. Now remember, I could also call this angle CED. The order doesn't actually matter as long as my vertex is in the middle. Okay, so when I look at that angle, I'm also thinking supplementary, and it will end up being 55 degrees because it's supplementary to that 125. last but not least, I'm taking a look at my final angle. My final angle is I'm going to call it DCE. And I know that angles in a triangle have to add to 180. My other two interior angles are 80 and 55. That means that the last one has to be 45 degrees. And I could justify that. Angles in a triangle add to 180. All right. Next example. Like I said, if you are feeling good about this, totally reject me. If you don't need me, that's okay. I will somehow find a way to get over it. All right, we're going to try and find the angle measures of these three angles, specifically XAZ, YBX, and YCZ. All right, and I'm going to highlight these as I go. So XAZ, X to A to Z is this exterior angle here. Now that exterior angle happens to be supplementary to that 55, so I'm looking at 125 degrees. So supplementary to 55 degrees. All right, looking at my next angle, I'm looking at Y to B to X. YBX. Okay, lovely. Now, this one, we don't know what it's supplementary to, and I suppose we could find out what it's supplementary to, but there is a shorter way. Today, we learned about non-adjacent interior angles, and we said the non-adjacent interior angles are going to be adding together to give me the value of that exterior angle. So I'm going to add 55 and 45 together to get 100. So I can easily find that angle in the shortest amount of steps. Like I said and mentioned in class before, it's not about how you get there, it's about getting there. So it's important to note that there are multiple ways. Sometimes there will be, sometimes there won't be. In this case, we can get there quite easily with non-adjacent interior angles add to the exterior angle. So that's specifically 45 and 55 degrees. All right, last but not least, we have Y, C, Z. This one is just straight up supplementary. I suppose we could use non-adjacent interior angles if we wanted to, but it's not the easiest way. So supplementary to 45 degrees is 135 degrees. That's what we got. Supplementary to 45 degrees. Woo! All right, last but not least, we are taking a look at this here, and we are trying to find the measures of angle A, B, and C. Like I said before, it doesn't matter how you do it, and it actually doesn't matter what order you do it in, as long as you could get there and justify your way. Now, when I'm taking a look at this, if you haven't paused and tried it on your own, please pause and try it on your own. Okay, welcome back. So when I'm taking a look at this, the first one that I noticed that comes to mind is angle C. And I know that angle C is supplementary to 75 degrees, giving me 105 degrees. So I'm going to write that down. Supplementary to 75 degrees. All right, so angle C is done. Now, the next thing I noticed is I might go, hey, hold on, how am I supposed to tackle A and B? I don't have not another supplementary thing. I don't got any parallel lines going on. But what I do know is that one key angle property is that I have non-adjacent interior angles sum to my outside, which means that angle C plus angle B are equal to 130 degrees. Well, I know what angle C is, which means I could figure out what angle B is. if angle C is 105, I have to add to 130 degrees. Then angle B is going to be 25 degrees. So I've got non-adjacent interior angles, specifically B and C. Add to the exterior angle of 130 degrees. All right, last but not least, I am looking at angle A. Now, I don't know what angle A is. Again, I don't have parallel lines. I don't have a full triangle here. And I could, I suppose, figure out what this angle here is using C or using my vertically opposite angle and then go from there. But the easiest way is, again, to look at my non-adjacent interior angles. So I know that 75 and A must add to give me C, which happens to be 105, which means angle A must equal 30 degrees. Like I said, it doesn't matter how you got there because there are multiple ways. But I do care that you can show me or justify how you got there. So here we have non-adjacent interior angles, specifically A and 75 degrees, adding to the exterior angle of C, which is 105. All right, and that's 2.2, talking about angle properties of triangles. Thanks for watching. Talk to you soon. Bye.